Thank you. It's a good question. Yeah, I'm not.
Okay, so our next talk is by Mahdi Soltanolkotabi from USC, and he's talking about another kind of non-convex optimization problems that actually connect to discrete optimization as well through the submodular maximization problem.
Thanks for the introduction and having me here. So, at this point, I think non-convexity has been well motivated, so I don't need to really talk about it. So when dealing with non-convex problems, we have sort of two set of approaches. One is based on convex relaxations and SDP hierarchies, and another, but we kind of do know that these ideas are not always perfect. Sometimes they're not very good in terms of memory, even when we have infinite RAM. So, and also sometimes they're not efficient in terms of data, meaning that sometimes convex relaxations, for them to actually work, you need more data samples. But then there is sort of a more classical approaches, which dates back to the 1800s, which is just following the gradient. And so most of what I'm going to talk about today is, what kind of guarantees can you get when you just follow the gradient? And as a side note, I actually think these two areas are much more related than one would think, but I'm not going to talk about this today. So I'm going to talk about this in the context of two problems. One is about learning very shallow nonlinear models, like very shallow neural networks. And then this one is the continuous one. And then I'm also going to talk a little bit about discrete optimization problems in this context. So in the learning the ReLUs, in particular, what I'm going to focus is on learning the ReLUs. So these are very simple nonlinear, non-convex problems. And hopefully the idea is that if we gain some insights into the convergence behavior of these nonlinear problems, and also sample complexity maybe is extendable to more nonlinear objects. So, so it's kind of the motto is deep learning but shallow thinking, but kind of happening anyway. So, we start from 0 hidden layers. So this is very simple. It's just a ReLU nonlinearity. You get to see the dot product of your data with your weight vector, and then you do a ReLU nonlinearity, max of 0 and x. So what I want to understand is what happens if you just use gradient descent to learn this nonlinearity. So you sort of have a sort of a teaching model. You have some W star, which obeys, your data obeys, is coming from a planted sort of ReLU model. And then you just want to understand what happens if you minimize the difference. And maybe you like sort of a regularization function, so that it's more generalizable or more data efficient in some way. So what you can simply do is sort of apply a projected gradient descent here, where the projection is onto your constraint sets. And the question one may ask is, what happens if you do this? So in order to sort of understand when this converges and at what rate and how many samples or observations you need to converge, it's good to compare this with sort of a well-known baseline, which is if we just wanted to solve the linear version of this problem, meaning there was no nonlinearity here, then we would be doing just a least squares fit to the data subject to your constraints. And then if you ask, okay, when is it that I can actually find the planted solution? Then there's very precise phase transitions for this. We understand this problem very well. So above a certain number of observations, you can precisely find W star by solving this sort of convex program. So I'm going to use this N0 quantity, which I haven't really defined, but as sort of a baseline on how many observations you need in this case. So if we go back to the ReLU model now, so again, we run projected gradient descent. If you assume your input data are Gaussian, then what you can show is that as long as you're a constant factor above this phase transition, then you basically converge at a geometric rate to the planted W star. And so in particular, if you know your W star, for example, to be like S bars in D dimensions, then this tells you that as long as the number of observations is above sort of a constant times S log D over S, then you converge at a geometric rate to W star. And this is starting from 0, by the way. So there's no sophisticated initialization scheme here. What is kind of interesting about this result that the fact that this regularization is convex is irrelevant. So this result holds for any regularizer. So pick your favorite regularizer. As long as you can project onto these sublevel sets, then this result works. So R does not have to be convex. It is anything you like. As long as you can project, then it's tractable. So
go back. Sorry.
Yeah.
Go back. So what do you? So it would be a linear inverse problem without the ReLU.
Yeah. So there's single.
Add the ReLU there.
Yeah.
The nonlinear inverse problem still works.
Still works. Everything is fine. And you just start from 0. No sophisticated initialization.
Is there a wider class than rather that you could?
Yeah.
The same thing?
Yeah. I mean, actually,
Aren't you a co-author on this?
No, I'm not.
I'm not talking about that.
I wasn't sure.
I'll talk about that if there's time at the end, but I don't think there's time. So,
It works a lot of stuff.
of course, there's a lot of silly assumptions here. So, one is like the input data is Gaussian. That you can really remove. That's not a big deal. Like the analysis goes through. Another one is, you might even argue like, why do you have IID data? That I also think eventually you can remove because, maybe you can replace sample complexity with more data-dependent sample complexity, like the kind of thing Sasha was talking about in his tutorial in the bootcamp. But I guess the more serious assumption here is like the fact that there is a planted model. In signal processing, we like to do this, and it's kind of valid. But here it's kind of weird to assume there is a planted model. And that might require more work. So I'm just putting it out there. Actually, Ben is surprising he has not complained about this yet.
What,
Like,
generalizability?
yeah.
You just make it, so wait, are you assuming it's not huge?
No, it is huge. It's just I'm assuming there is a planted weight vector, right? So it's kind of weird to assume that, but what are you going to do? So.
Or doesn't just have to exist one? Sorry, I'm confused by that.
So I'm saying like I'm assuming there is a W star, and then I'm drawing data at random. So that is a little bit weird. Yeah, there's a unique one.
You're not. Are you assuming there's a unique one, or just that there exists one?
Yeah, there exists one. Yeah. So it's a planted model basically. But anyways, so just to also mention.
Sorry about that.
Yeah.
So all you're saying is that.
It's like a compressed sensing model.
But like, are we just asking for existence, or no?
Well, you assume there is some W star, which you have some W star, then you draw the model, the Gaussians at random, and then that creates your output, right? It's not like you have pair of inputs and outputs, and then you try to find W star.
These are first one.
Yeah. So of course, like learning ReLUs is not really difficult because there's a bunch of other methods that can learn ReLUs because it's, but they're not about just projected gradient descent. So kind of the idea here is we just want to understand what happens if you just learn them via projected gradient descent. But because they're monotonic functions, there's all this literature in the statistics literature on learning single index models, and more recently there's also been some work about learning ReLUs using kernel methods. But the point is just let's understand what happens if you use gradient descent. So that's kind of the idea. Let me briefly mention how this kind of proof works, because I think that's kind of an interesting connection, which is the way this proof works is it basically connects, characterizing convergence rates of non-convex gradient methods to supremum of stochastic processes. And so if you can make that connection, then there's a bunch of tools we could potentially use to do this. And so the idea is very simple, but it actually works. So the idea is if you have your iteration, so WT is like project onto your constraint set, you do one gradient iteration, or your loss. So if you look at this minus W star, so if you kind of look at the 2 norm of the error, the idea is that hopefully you want to show that the 2 norm of the error goes down at every iteration. So you want to show something like this. You want to show this is bounded with a constant. And so if you can show this, then obviously you get convergence. And so what happens here is that actually you can replace this just by the fact this is 2 norm. You essentially write the 2 norm as supremum of something. So it's kind of like you write this is as supremum of U transpose WT plus 1 minus W star over this. Now because this is actually a projection onto K, what you can do is you can take the supremum only inside a sort of a cone. This cone is essentially like the tangent cone. It's like the conic hull of K minus W star. So now what happens is what you really have, you have a stochastic process as a function of U and any general vector in W. So you can really think of this as you're trying to bound something like supremum of X and WT minus W star, and the supremum is over U inside some cone, and then WT inside some set K. So as long as this quantity is random, so you can use tools from stochastic processes to try to actually bound this. It's not so easy. Sometimes you have to do generic chaining and things of that sort, but essentially that's the idea. So you can learn something about convergence rates of non-convex problems by bounding stochastic processes. That's kind of the rough idea. And I just, because I am looking at a random model, I just want to mention that it is sometimes dangerous to just think about random models. So in particular, one popular paradigm these days is that local optima are global. This is why gradient descent methods converges, and the answer to that is really no. Local optima are not global. So this is not about learning ReLUs, but a very closely related model. So I just wanted to put this out as a warning. So you have different local search heuristics. All of them are known to converge to local optima in this problem. And what you see is that basically all of them converge to different local optima. So not only are there a lot of local optima, they're actually sometimes very close to each other. So this is basically about learning absolute value nonlinearities. So this is sort of gets me to the motivation for the second part, which is, okay, maybe we don't want to assume random models, but can we then, if we assume all things, the data is deterministic, can we show some sort of approximation guarantees for gradient descent, right? And I'm going to do that in a context of a different problem. So we're not going to try to assume any randomized assumptions, but instead of showing convergence to global optima, we'll show convergence to something with high quality in some sense. And so I'll do that in the context of submodular maximization. So, and in this part is joint work with Hamed Hassani at UPenn and Amin Karbasi at Yale. And just another acknowledgement, all of these results were done on the boards of assignments from last semester. So, this problem is about set function maximization. So this is a discrete problem in nature, but you'll see you can transform it into a continuous problem. So essentially the idea is you have a bunch of items. You want to pick a subset of these items that are in some sense most informative. So what you have sort of is a ground set. You have sort of a scoring function that assigns a value to each subset. And then you want to maximize over all subsets, maximize the scoring function. So that's kind of the idea. So submodular functions are a particular class which are characterized by sort of this diminishing return property in the sense that if A is a subset of B and you add a single item to A, then the value you get out of adding this item to A is bigger than the value you get out of adding this to B. So if you if you have a berry food already, adding like a blackberry might not be very better than if you don't have berries, right? So that's kind of the idea. Contemporary things of interest is sort of in big data summarization. So if you want to pick a subset which are more informative in some way, you can cast a lot of these problems as submodular optimization. And I think something that maybe not a lot of people have looked at yet, there are a lot of cool problems in optical design, where if you want to pick informative measurements among a particular class, then you can also use submodular ideas there. But this is not something that I think has been looked at this, but so it's also very useful in computational imaging when you want to sort of design your modern imaging systems. I think there's been a lot of talks on this already, but let me just do a quick recap of what is known, so that maybe like our results fit better into by that context. So one particular class of submodular problems that a lot of people have looked at is sort of monotonic functions, which is if A is a subset of B, then f of A is less than f of B. And in particular, one is sometimes interested in sort of maximizing monotone functions with a cardinality constraint. So in addition, you want to not only pick an informative subset, but you sort of have a maximum number of elements that you want to pick. So in this context, there is sort of a famous greedy algorithm, which is a very simple algorithm. Essentially, you start from 0, you add the most informative item, and so on, and you repeat. And so there is very good approximation guarantees for this algorithm. In fact, you get 1 minus 1 over E approximation ratio. And it's also known that you cannot do better. But outside of monotone for functions, essentially the greedy algorithm, there's many famous examples that it doesn't work so well. So you often, for general problems like matrices and so on, there was a lot of talks on this in the last workshop. This doesn't work well. So what people often do is they go to the continuous domain. So essentially, one studies continuous relaxations of this called sort of the multilinear extension. And the idea is that you sample each entry according to probability xi, and then you take average with respect to this random subset sampling. And so essentially what you're looking at the discrete problem of memberships, which is like a 0, 1 vector, as sort of a continuous vector x, right? So that's, there's a lot of averaging here, but this way you sort of transform the problem into a continuous problem. And what is known is that if you can solve this, the optimal solution is a discrete point, and so if you can solve this, then you can solve the original problem. So one can try to solve this instead. And so there's a lot of interesting algorithms on how to solve this. So one particular one is sort of the continuous greedy method, which gets very good approximation ratios. So this you can, for the continuous people in the audience, you can think of this as sort of a variant of Frank-Wolf, essentially. But it's a very smart variant that is designed for this particular case. And again, under various assumptions, there's a lot of approximation guarantees for this, and this is really very nice literature on this. So in particular, in the monotonic case, this is also known to get 1 minus 1 over E approximation ratio. But I'm going to use a slide from one of the speakers in the last workshop, where one issue with this maybe is that you need, you never know this continuous function f. So because it's an average of a bunch of things. So in practice, you don't really have access to it, but you can basically sample and basically get an empirical average, and you have to use that. And one issue with some of these continuous methods, and in general, what could happen is that you might not even have access to the original function itself, in the sense that it might be already an average of a bunch of functions. So you might already have sort of a stochastic setting where the number of sub-functions fi could be very large. So in any case, you might not even have access to the discrete function, let alone like the continuous version. And this happens in a lot of so whether it's data summarization or influence maximization problems, this happens a lot there. And then, if you also do the continuous relaxation, then there's another sample complexity issue. So the point is that you would like to have algorithms that can be stochastic, right? And in this setting, so if you try to do this with Frank-Wolf kind of algorithms, it's not very amenable to being stochastic, and I'll mention why. So when I saw this continuous extension actually in the tutorial from the last program, I got curious, what happens if you just run gradient descent on this continuous extension, right? So, and this is one of the questions I asked from one of my friends, which ended up being a co-author, is what have you tried gradient descent? And so what I mean by that is you want to maximize some continuous function. Let's just do a projected gradient descent. So in the case of cardinality constraint problem, you do a gradient ascent, and then you project onto these cardinality. So basically, you project onto portions of the simplex, essentially. And as I said, this could have the added benefit that if you're kind of in a stochastic setting, then we know that projected gradient methods are very easily, you can develop stochastic variance. Whereas like the continuous greedy methods, it seems that you can actually cook up examples where the stochastic variant fails. And we have one such example in the paper. And essentially the idea is that averages and maximization don't go well together, right? And so if you have sort of an empirical average or a sample, like a stochastic version of the gradient, then the Frank-Wolf kind of algorithms may easily fail. Whereas, for projected gradient methods, it's very easy. You just have a stochastic sample, you just run stochastic gradient descent. So let me tell you about some theory that we have for these problems, but this is very limited, so it only applies to a very limited class of problems, but hopefully we can extend it. So the theory we have is for the most general case of continuous submodular optimization problems, which are called weakly DR submodular. Essentially, these are all problems where the gradient of f of x is bigger than some gamma gradient of f of y when x is entry-wise smaller than y. So the particular case of gamma equals 1 is sort of the continuous extension of normal submodular problems. So gamma equals 1 is what you would get if you extended discrete submodular problems. And a particular focus, as I said, is on really stochastic problems for us. So the first kind of simple result is that all stationary points have a very good, well, not very good quality, but have at least some good quality. So this is what I mean by stationary points. It's sort of equivalent of gradient equal to 0 for when you have constraints. So if the function is monotone and gamma weakly submodular, then what you can show is that all stationary points have sort of this approximation property. So in the case of gamma equals 1, this becomes 1/2. So it's not 1 minus 1 over e, but it's something like, well, it's at least something. And of course, you know that if you pick a very small step size, then you can also perhaps converge there eventually. It's not clear at what rate, but you know that you can converge. So I do like to point out that this can be viewed as a very simple extension of results that is known in the literature. In particular, for the experts in the audience, the case that it's gamma equals 1, this is sort of an immediate consequence of this lemma that it often appears in the continuous greedy literature. So just wanted to point this out. So, but our focus is not really just studying the quality, but it's how can you get there, and can you do this in a stochastic manner? So first of all, let me talk briefly about the approximation guarantee here, which is 1/2. The bad news is that there are counter examples that basically there are examples that show that you cannot do better than 1/2. So if you want to start from everywhere, you can actually construct local maxima that have approximation ratio 1/2. But if you start from other points, in particular 0, what we've observed that it always works very well in practice, and we have not seen any instance that it gets worse approximation ratio compared to greedy or continuous greedy methods. We have some ideas how we might be able to prove these things, but not very concrete ones yet. But again, our focus is really on developing stochastic variance, and so this is kind of what we can show is if you do projected stochastic gradient methods, in the sense that if you have access to a stochastic oracle, which is unbiased and has a certain variance, then if you do stochastic gradient methods, projected gradient methods, then that has good approximation properties. And so the running time is surprisingly similar to what you would get out of a convex optimization problem. So you have like 1 over epsilon, and then you have like sigma square over epsilon squared. Yes?
Were your guarantees for cardinality constraint or general feasibility constraint?
Sorry?
Was the guarantees you had for cardinality constraint equal to k, or for...
So this is for any convex constraint. So this is arbitrary. As long as it's convex, then yeah. And there's also mirror descent variance of this, which is actually very helpful in theory at least. So you can repeat all of this using a mirror descent scheme. And the reason the mirror variant is important is because essentially you can measure smoothness in a different norm. And for example, for cardinality constraint problems, what you would get for the Lipschitz constant is like k times the margin of f, which is like the maximum value of a single item. And so the running time would be like k over epsilon and only logarithmically dependent on the number of items. So if you know some of the continuous greedy literature, usually this dependence is much, much heavier on the number of items, like n4 or something like this. And so at least in terms of the number of iterations, those dependencies go away. Here is sort of some simple numerics to demonstrate that at least it's competitive with baselines. So this is a very simple example where you only have monotone score function. So this comes from sort of a recommender engine application where you essentially want to pick like the top k informative movies to show to the user. Essentially, that's kind of the idea. And so that we do various scoring functions. And so greedy, obviously, because it's monotonic, greedy works very well. But what this plot shows you that projected gradient descent with very few iterations actually can achieve the same basically the same objective value as the greedy algorithm. And this plot also shows you that the stochastic variance is very much competitive with stochastic variance of continuous greedy. In fact, continuous greedy seems to be converging to a different local optima, which is worse. And this also tells you that the stochastic variance in terms of total oracle calls to this function f is also competitive with greedy algorithms. Another maybe interesting experiment here is because especially I'm more from the continuous side of things, and we're kind of used to solving max cut problems using like the SDP approaches, but you can also use this gradient descent on the multilinear extension. And the interesting part is in some of these graph problems we actually observe better approximation ratios if you just do gradient descent on this continuous extension. So it would be cool to study what happens even in this particular cases.
What is the number there? What are these numbers?
So these are just the objective value. There's a max cut problem, higher is better. So these are like, this is from the old, the classical papers where you apply max cut, and these are the objective values you would get out of them. So let me do a quick recap. I think I actually have a lot of time, right? Or no?
Yeah.
Yes, 13 minutes.
So I can go into the deeper stuff. So let me briefly mention those. So slightly deeper is in the neural network businesses. If you had one hidden layer, right? So you have your input. You have your input to hidden layer, and then you also have an output layer. So one hidden layer. So the formula will look something like this, and then you have some nonlinearity in the middle. So our result in this space is very preliminary, but at least it's kind of deterministic. So there you would want to fit a nonlinear model like this. You want to minimize over both sets of weights. And we would like to understand the properties of this optimization problem. So far what we've looked at, we have some results for other nonlinear models, but they're not as strong. So let's say a very non-realistic quadratic model for phi. Of course, this is not realistic, but the results are somewhat insightful. So we look at this optimization problem in the following context, which is we assume the problem is over-parameterized. So the input dimension is d, the number of hidden units is k, and the total number of samples you have is n. So this problem is over-parameterized in the sense that the number of observations is less than a constant times kd. So you have actually more parameters than the number of observations. This is actually the regime where neural networks are trained usually. And the network has to be wide in the sense that the number of hidden units is at least twice the dimension of the input dimension. Then for this, in this setting, and the cool thing about this is completely deterministic result, what you can show is that all local optima are global, all saddles are strict. There's a direction of negative curvature, and so which implies that gradient descent converges to the global optima. So this is optimizing over W only. We assume like the last layer of weights are picked completely random. So this is, so far everything I said is deterministic. You always converge to the global optima. But of course, this doesn't tell you that the quality of that global optima is good. And for that, you do need some sort of diversity assumptions, because if you just repeat your data set, obviously you cannot fit just repetitive data with very good accuracy. So if you assume some generic assumptions about the input, like let's say if the input data is Gaussian, then you can also show that error is in fact 0. So that's kind of the idea. And we have some results about more realistic nonlinear models. Oh, this, by the way, is with Adel and Jason, colleagues at USC. I forgot to mention that. We have some results about other nonlinear models, but they're more local in flavor. So we don't have global results. But we do believe that in practice, it does seem to work like this, right? Like we do get 0 training error. So just quickly mention some related work in this space. So for training shallow neural networks, there's sort of a lot of recent results. So there's kind of 2 flavor of results that let me directly compare with. So one is there's a lot of interesting results, including by people in the audience, where they do look at overparameterization, but it often requires more overparameterization in the sense that instead of assuming n is less than a constant times kd, the assumption is usually the number of data samples is less than the number of hidden weights, but basically hidden units. So it allows, it requires more overparameterization than us. So that's kind of the major difference. We can get away with very modest overparameterization, right? So it's like a constant factor from the total number of parameters. And there's also, there are a bunch of interesting results in the other regime where you have more observations than the number of parameters. Again, this is not exactly the regime where neural nets are trained, but so in this setting, there is a lot of local convergence results where you show that if you start sort of close to the global optima and you just do gradient descent or a resampled gradient descent, then it converges. And so this is this class of problems. And there are many others using other methods other than gradient descent if you use tensors or kernels and so on. So there's a lot of interesting work in that space also. So with that, let me conclude quickly. So a quick recap. I talked briefly about learning nonlinear models, including shallow neural networks, and also stochastic approaches to submodular maximization. And my research over the past few years have been really following this question of have you tried gradient descent? And so it started in the context of some imaging problems, and now I'm looking at the sort of more nonlinear problems. And so here are some of the references on sort of non-convex problems that I've been working on. So let me end here.
Okay, we have plenty of time for questions. Any questions?
So the max cut problem you showed is a non-monotone submodular function, right? So do you still have to start at 0, or like your results? Do they extend for that case?
No, not yet, but eventually we hope. So as I said, our results is very limited. It's just focused on monotone and just monotone problems at this point. But we hope to be able to extend it slowly.
So for the max cut problem, you just did numerically?
Yeah, this is just numerics, yeah. We were just curious because it's different from the normal paradigm I'm used to, which is we do like low rank factorization to solve max cut, like at least in the continuous literature. So we were curious, how does it actually work?
What is the time comparison?
So I mean, the STP numbers I took from the papers, I have no idea. We didn't run the STPs ourselves.
Any other questions? Okay, so let's thank Mahdi again.